Okay, actually, I put these two bottles down here with balloons on them because I wanted the heat of the sun to blow up the balloons for me. And when I started, they both looked like that.
Deflated.
Yes. Which one is the best conductor of heat?
Black one,
The black
because,
one,
yeah, it's the black one.
Okay, so what I wanted to show you with this was that if you have a nice black object and you have air inside, the air inside that black object is going to be heated because the black absorbs the heat of the sun. Okay, over here, you see that black bag I have over here?
Yes.
Well, come on over here. What I want you to do is help me hold it open so we can fill it full of air, just the wind blowing it in.
Okay.
And then I have some thread in my pocket, and you grab it all together like this, and then we'll tie it off.
Okay. Sure.
Okay, now quick, grab it all together. I'll get out my thread.
Okay.
Okay, now let go.
It's rising already.
Yes. Now why? Why does it go up?
I bet it's because of the hot air inside it being warmed from the sun and being black that makes the hot air go up.
Actually, it's the air around it that's cooler, right? And it weighs more and is pulled down by gravity that forces the warm air up. So it's actually the air around it that's forcing, like a bubble in water. When you let go, the bubble goes up to the top. Here, you want to play with it?
Sure.
It's all yours. Try not to get it in the tree, okay?
Okay.
This common mystery object illustrates one theory of how some of the Earth's mountains were formed. Once this was a smooth surface, but the material below it shrank, just as the molten inner part of the Earth did as it cooled. The outer skin buckled and folded, forming the mountains on the surface of a decaying apple. There are various kinds of mathematical games in which you pick up sticks or toothpicks or matches. I assume you played one. Here's one that I like to do with checkers, although matches and toothpicks would work. And the object of the game is do not pick up the last one. Whoever picks up the last one loses.
Okay.
And here are 3 piles of 15 checkers altogether, 3 piles of 5 each. And you have to take 1, 2, or 3 when it's your turn.
Okay.
So go ahead, you start.
All right. Take 2. I lost.
You lost.
Okay.
Let's do it again. I'll start.
Okay.
See if that makes a difference. Okay, I'll start.
I lost again.
You lost again. Now, the secret is very simple. And you notice how quickly I was able to move, regardless of what you did? That's because I was following the pattern. Okay, here's what you do. Whenever it's your turn, you leave your opponent with 13, 9, and 5.
Okay.
13, 9, and 5. That's why they're in nice piles of 5 each, so you can quickly count. If I take the first one, what do you take?
I'll take 1 to leave you 13.
Right. If I take all 3, you do what?
Take 1 to leave you 9.
If I take 1 here,
I'll take 3. And
that leaves me with that. And regardless, if I take 3, you'll take 1. If I take 1, you'll take 3. If I take 2, you'll take 2, and you'll win. So this is a very frustrating game that's easy to do. Who are you going to try it on?
I think I'll try it on my sister.
Okay, just make sure you understand now. What are you going to do? If I take 2...
I'll take...
Go ahead, take anything. But the next time, now make sure you take 9.
Okay.
Okay, so leave 9. If I take 2...
Take 1.
Okay, if I take 3...
Take 1.
And if I take 1...
Take 3.
And I lose. Okay, good luck.
Oh, thank you.
It's been more than 12 years since astronauts last visited the moon. Now, because of the success of the space shuttle, the National Aeronautics and Space Administration is planning to launch a permanent manned space station in Earth orbit. Once it's built, the next logical step will be to return to the moon. Already plans are on the drawing board for a permanent base there. It's an ideal place for scientific research, like radio astronomy, and for organizing expeditions to other planets. But to build a moon base will take raw materials, which could come from the lunar soil. You see, the astronauts collected samples of rocks from the moon's surface. These precious samples were carefully analyzed and found to contain elements that could be very useful in constructing a moon base. Oxygen might be extracted for breathing, along with iron and other metals for building materials. At Washington University in St. Louis, long-range research has been underway to learn how to extract useful raw materials from moon rocks. The wire hanging from the tube on the right contains a thermocouple, which measures temperature. The raw material in the left tube is a blend of earth minerals that duplicate the composition of lunar rocks. The two tubes are placed into an electric furnace, which will heat the sample very quickly to a high temperature. The furnace is started. Through an observation window, you can see the sample melting. When it does, an electric current is sent through the sample to separate the components. The sample is removed from the furnace and quickly cools. Later, Dr. Larry Haskin uses a copper saw blade studded with diamonds to slice through the sample. He wants to get a slice right through the center where the reaction took place. Several slices are mounted in a special holder and then inserted into an electron microscope by Dr. David Lindstrom. Instead of taking pictures like a light microscope, the device uses X-rays to analyze the chemical elements in the samples. The spike means iron was successfully separated from the simulated moon rock. Of course, in the years ahead, much research will be needed for scientists to perfect the techniques on Earth that will be used to mine raw materials on the moon.
Nice siren sound, right, Eugene?
Right.
If you consider a siren sound nice, it's sort of an awful sound, isn't it?
It's really
Now, do you know how it works? What makes the sound in the siren?
Well, probably because while these things are moving through, these blades, they slice through the air.
Well, that's partly true, but the important thing is that they force the air out through these holes that are alongside here. See, as it turns like that, it forces the air through the holes, and the holes vary in size as the thing spins, right?
Yeah.
See how now it's big, and then it gets smaller and smaller and smaller, and then it closes off completely, and then it starts smaller and gets bigger and bigger and bigger. So as this goes around, it chops the air into little tiny pieces that are constantly varying in size, and that's what makes the horrible sound of a siren. Now, how did the sound get from here up to here?
Well, when the thing went around, right, it chopped up the air.
Yeah.
And the air was vibrating, and it brings the messages or the sound to your ears.
It goes through the air over here. Well, now here is a bell jar with a vacuum gauge on the top, and here's a vacuum pump. You know how to work a vacuum pump? You turn it on over here, and here's a little clamp. We'll start the siren going. Then, first of all, I'll put the bell jar on top. So now at least we've got it covered with glass. After I turn it on. Then I want you to turn on the pump, and that'll pump the air out from inside there. Then after you got it turned off, when you watch the gauge, and when it stops moving, you'll know you got a good vacuum. Then you can close that clamp. Then you can turn off the motor, and everything will be quiet, and we'll hear to see if we can hear the siren. Do you think we'll hear it?
Well, maybe.
Maybe? Okay, well, anyway, you get the idea?
Yeah.
Put on the safety glasses, because we're taking the vacuum, we're drawing all the air out from here, and we don't want that glass thing to implode and possibly fly glass all over the place. Can you hear it?
Yeah?
Okay, now that's with, how's the sound getting to your ear now?
Well, the air is hitting against the glass,
Right.
which vibrates the outside
Right.
of its atmosphere, and the outside air travels
So
through
it's
the
going
ears.
through the air inside the bell jar, then it's hitting the glass, and the glass is vibrating this air, and that is vibrating your ear. Okay, now turn on the pump. Watch up here. Okay, we got a pretty good vacuum. Okay, now you can turn the pump off and listen.
You could still hear it a little.
Hear it just a little bit. Probably because it's coming through the table, because it's vibrating the table and eventually coming up here. Now, what should happen when you open the clamp?
Well, all the air would go out, then you could hear more of it.
Should get louder, right?
Right.
Okay, try it.
Louder.
Yeah, it got louder. And what'll happen when I take this off?
It'll get louder.
So the whole reason for doing this experiment was to solidify in your mind what it is that's necessary for you to hear a sound. What is it?
Well, some kind of substance to carry the sound.
In other words, sound has to go through something. In this case, it was going through air, or through glass, or through wood. But in order for sound to travel, it has to have a medium of some kind. In this case, it's air, right?
Right.
I have a kind of a tricky little problem for you, Stacy. Let's assume that you applied for a job,
Okay.
and you said, I would like to make $20 a day, and you're going to work for 20 days. How much would you make in it?
$400.
And your potential boss says, sorry, Stacy, that's much too much money. So then you make a proposition back to him. You say, well, pay me only a penny the first day.
Okay.
And the second day, you pay me 2 pennies. And the third day, 4 pennies. In other words, doubling each day. At the end of 20 days, would you be money ahead?
I think you would be.
Well, how? How come?
Well, one time in math we had this problem. There's a bacterium in a jar, and they double at the rate of they double each day. And at 20 days, it would have filled the jar. And at how many days would they have filled half the jar? And most people think 10, but it's really 19.
Okay. The idea of doubling a number, you soon run into very, very big numbers very, very quickly.
Yes, you
In fact,
do.
I have worked out what you would get each day and
Okay.
covered it up so you couldn't see it. So push it down there, and you see here's day 1.
Yeah, you get 1
1
cent.
cent.
Then you get 2 cents on day 2. It's doubling, so you get 4 cents, 8 cents, 16.32. Then, for
Starting getting pretty big right away. 15th, 16th, 17th day,
Oh, my
18th,
goodness.
19th. Here's the 20th day, and I even went one beyond to the 21st day. So on the 20th day, what would you get?
you get $5,242.88.
Now, that idea of doubling, scientists use it quite a bit. In the case of bacteria, doubling every 20 minutes. Or other kinds of animals that have a life cycle maybe of once a day or once every week or something. And they use that doubling idea in order to calculate the total number very quickly. But you would not receive $5,242.88.
wouldn't.
No, because you would actually have the total of all of these.
Oh, yeah.
So really what you have to do is add all these up. But there's a simple way to do it. Notice, by the way, that if you add the first day to the second to the third, you would have what?
7 cents.
And notice that's 1 less than doubling the next day and subtracting 1.
Oh, I see. So you double the 4 cents and subtract 1, and you
And
get
you,
7.
and you get the total. So now you go down here to the 20th day,
Oh.
and I've already done it. I've
Yeah.
doubled it. So what do you actually receive?
$10,485.75.
Yes. And that's a quick way to add up a column of doubled numbers like that. In fact, you would be money ahead, right here?
Yeah, about the 16th day, because I'd have $655.35.
Right. So that's kind of an interesting problem.
Yeah,
you
that
try
is
that on your
really-
dad. See if you can get him to pay a double every day. And see
Yeah,
how
for
soon
my
you get.
allowance.
All right, good idea.
As you fly over the shallow water around Florida, you can look down and see some of the most unusual mammals in the world swimming just below the surface of the water. You can see why sailors of long ago thought they were seeing a mermaid, that mythical creature with the head and body of a woman and the tail of a fish. But when you get a close-up look at its face, the creature is obviously not a woman. It's a manatee, whose face resembles a cross between that of a walrus and an elephant, without the tusks. With its muzzle, it grasps food in somewhat the same manner as an elephant uses its trunk. Its eyes are similar to an elephant's. The nails on its flipper look very much like the nails on an elephant's foot. Scientists believe that both the manatee and the elephant share a common ancestor many thousands of years ago. Those that took to the water evolved into the manatee. They must come to the surface to breathe air about every 3 minutes or so, but can stay underwater as long as 15 minutes. Like all mammals, the calf gets milk from its mother. Her nipple is located just behind her flipper. Even though the gentle manatee has no natural enemies, there are only 1,000 or so left in the world. At one time they were hunted, but now are protected by law. Their biggest problem is boats. The manatees like to bask just below the surface where boats can accidentally run into them. The Florida Department of Natural Resources posts signs to alert boat operators of the manatee's presence. Another problem is the growing population of Florida. As cities expand, the shallow waters the manatees prefer can become polluted. But the manatees have adapted to the changes man has made in their environment. A survey by the Florida Audubon Society found that during the winter, manatees collect in the warm water released from large power plants. They're only been seriously studied by scientists since 1960. If they are to survive, much more will have to be learned about the gentle giant, the manatee. Have you ever seen one of those, Chris?
No.
Well, you've looked down to the side of a toaster and seen the sort of red wires that are there?
Well, a few times.
Yeah, but anyway, you know that you can send electricity through a wire and it creates a heat. And that's what this is a heat source. Ordinarily, it's in a reflector like this and it sends out heat. Take this plastic straw and just place it right on the top.
Gee,
As you
it's
can
melting.
see, it is a source of heat. All right? Okay, now we're going to use that as our source of heat. So come around over here. I have 2 cans. Before I bring this heat over, notice how they're different?
Okay, yeah. The black, on this can, the black side is facing in, and on this side, the shiny side is facing in.
Right. Which one absorbs heat best, do you know?
I think the black.
Why, do you know?
No,
Well,
I
black,
don't think so.
black by definition is the color that absorbs all the wavelengths of light and heat, while the shiny side reflects them. So if I bring the heat source over here, see that little bead?
Yeah.
Okay.
Is that food coloring?
That's food coloring, right. If you place the heat source here, what should happen?
Okay, I think this should move that way
Why?
because the heat source is over here.
Okay, and that would this would absorb more heat up the air inside here, and the air would push the dot over this way. Okay. Then if you put the heat source over here,
Then it would go that way?
all right. Okay. So it's up to you now to move the heat source in and out, and handle it by the bottom so you don't burn your little fingers. Okay. And bring it in there and watch what happens. Whoa!
Ooh.
Bring it around over on this side. Okay, what do you do? Quick. This is called a thermoscope.
Takes a while to heat.
In other words, it tells us something about the temperature of the air inside there. Bring it over here quick. And it's very sensitive, isn't it? Mm-hmm. Also, you can see there's a great difference between the black side and the shiny side. The black absorbs more heat, the shiny side reflects it. All right, now, wait a minute. Pull it back out of the way.
Okay.
I want to turn the cans around.
Okay, should I turn this one
Yeah,
around?
turn that one around. Now what do you have to do?
Okay. Okay, it seems as you turn the cans around, and the black is facing this way.
Watch your finger.
Now,
Watch
when
your
you put it
hand.
in the bottom, it would do the exact opposite thing.
Okay,
And
put it in there once and see.
Oh, okay, it goes that way.
Okay, now quick. So it's a very sensitive device that shows the difference in heat and light absorption of black and shiny. What's the most famous poem about stars, Bibi?
Twinkle, twinkle, little star, how I wonder what you are.
Yes. Have you ever seen the stars twinkle?
Yeah, sure. I look at them every night.
Yeah. Do they look like my stars over there?
Yeah,
See how they're twinkling?
neat.
Well, I'm making my stars twinkle in the same way that real stars twinkle. Come on over here. I'll show you how I'm making my stars. Here is a regular 35mm slide with aluminum foil in it. And you poke little tiny holes in it, and when you project the light from the projector through it, you can project stars up on the screen.
But they're not twinkling.
Well, the reason they're not twinkling is, you see what I did? I moved this out of the way. I'll put it back in position. And it's electric stove. So now, do they twinkle?
Yeah,
Why?
because the light is passing through the heated air.
The heated air, right. When you heat up air, in this case with a stove, well, you change the density, so as the light goes through, it's bent with the changing density. You've seen that, haven't you, on a highway when it's a hot day and you drive
Yeah.
along, you can see heat wave sort of thing? Yeah.
When we have bonfires, I always look through the fire and it's always
You can
wavy.
see it wavy like that, too.
Yeah.
Well, but now there's not an electric stove heating up the air.
No.
At night, what is it that changes the density of the air?
The atmosphere of the earth.
The atmosphere itself is made up of various densities of air. So as it changes, that's what makes the stars vary in density like that.
Yeah.
Okay, so now, what's that poem again?
Twinkle, twinkle, little star, how I wonder what you are.
Okay, you can change it now to what? Twinkle,
Twinkle,
twinkle.
little star, now I know why you twinkle.
Well, it doesn't rhyme, but it's accurate.
Yeah.
Right? Very good. Here's an important secret message which I'm sending to you, Stacy. Can you read it?
No, I can't.
Well, that's because it's in what I call a zigzag code. You must have made codes, haven't you, at some time or other?
Well, yeah, when I was little, we used to do a code that A would actually mean B and things like that.
Yes, that's called a substitution code, which you substitute some symbol for the message, but the message is right straight across once you make the substitution. Well, there's another whole group of codes in which you take the message itself and scramble it in some way. Some of them are very complicated. This one is very simple. All you have to do, in this case, is put the first letter down here and the second letter up above and make 2 rows, and you'll be able to read it. Go ahead, try it.
Okay.
You read my message?
Yeah, it says arrive at 5.
Arrive at 5. Should be a little space right there, but you
Yeah.
can soon tell that, right? Okay. Now, it's as I say, that you can make much more complicated codes in which you can have the whole message, then you break it up into groups of 4s, and you put one from each row into the scramble. And it gets really very complicated. I made this simple one just to show you the idea. Now that you know how to do it, you can put it back into code, can't you?
Uh-huh.
And now also that you know the secret to the code, you can see why I called it a zigzag code because of the up and down. And you probably don't even need to break it down. You can probably read it now, can't you?
Yeah.
Arrive at 5.